Um, Sorry about the technical problems, but
Sorry.
welcome our next speaker, who's Haixing Li, will speak to us about regular representation and AN/AM bimodules. Okay, so thank you very much.
Okay, thank you. Sorry for this technical problem. I just recently got this new computer, so I didn't know the system here. Okay. So from the title, you see that two parts. One is regular representation. The other part is about the bimodule. So regular representation actually is a kind of already little bit old stuff. Okay, so I will start with a quick brief statement about regular representation here. Oh, that's a long one. Okay, so for vertex algebra V, so what is the regular representation? So regular representation, so associated to a weak model, W, and a complex number, non-zero complex number, Z. So this is constructed inside the Futorny space of W star, and it's a weak V tensor V model for that. And this model and has a deeper connection with the Heluani and Lebowski construction tensor product. And more precisely, we can say, so for V3 models, so a linear map F, so it's a PZ intertwining operator in the sense of Heluani Lebowski, if only if this F, the image of that F inside this so-called regular representation, and F exactly is a V model homomorphism for that. So in case of a W equal the adjoint model, and then we can show that all the irreducible V tensor V submodel inside there of a circle and has a Peter-Weyl decomposition. So that's why we call regular representation for that. So in the past, so we use regular representations to revisit Drew's AV theory and also Franco Drew's fusion rule, also ANV theory for that. So one philosophy, roughly speaking, one is the construction of this weak W, V tensor V model, and also as well as Heluani and Lebowski construction tensor product models are kind of a global approach. Global here means theoretically constructed models. And compare with Drew's AV theory and its generalizations. So basically, this is use substructures and then use induction. That is a local approach. So in Drew's theory, the proof of Drew's one-to-one correspondence or Franco-Drew's fusion theorem, global to local direction, and from model or from intertwining operator to AV model or AV model morphism actually relatively easy, actually much easier than the other direction. The other direction from local to global is much harder than that. So at this time, the regular representation can help us to make the other direction also much easier because naturally we have model or weak model. So that's the idea. And the key for this application is that, and we have AV as a quotient of V. We also have AW as also quotient of AW. And the dual space of AW actually exactly equals the so-called vacuum space of this V tensor V model. So that's the key. And in 2008, and Chongyan and Jiang and developed this system further. So talk about ANV, AMV bimodal, significantly generalizing the previous ANV theory in a new direction. And this is to provide a more refined tool in study representation of that. And the current work so basically means, so we want to use a regular representation as the main tool to examine the theory of joint. And basically we give a canonical identification of vacuum space for regular representation. And with this is Zhenjiang ANV bimodels. And also this in several places obtain new proofs for some of their results. Another thing I just quickly mentioned that in the abstract, in the last sentence, we mentioned that the character stuff. Here I just mentioned that I will not have time to talk about detail in this talk. Also, not closely related, but this only relate to a regular representation. So for any V model W, we consider the Q-graded trace function as a function of V. So the coefficients, the Q powers coefficients, all are contained in the regular representation. Here, Z equals -1. And also, if W is irreducible, those coefficients generate a V tensor V submodel. Actually, it's irreducible. That's the V W tensor, the dual of W. So this is irreducible. So this is very interesting. This is to tell you that from irreducible character, we can directly construct an irreducible model. Okay? So basically, this means indeed irreducible model can be canonically determined by irreducible character. Okay, so this is the rough introduction. Now, I will go, the first part is about A and V, okay, the associative algebra. So I will, yesterday in Karina's talk, she already mentioned AV algebra, everything, so I will just do this quick. So first, let the W be a general weak model and a non-negative integer. So we define the first star for product. The second circle basically defines certain elements defined for the quotient space. So that. Okay, the formula looks technical. So say the first one is the product related to n, the second part just to give us some vectors. So we want to get the subspace. So ONW exactly just those V circle and W, and also together with the image of L-1 plus L0 now. And also in the congruent model theory, also in Bruce's theory, we have this as an anti-automorphic thing. This theta can be defined globally from V to V and just exponential L plus 1 and -1 to L0. That. And this simple fact, square equal 1. So here's the result in A on V theory. And there's a non-negative integer. Then the star multiplication is defined for the whole V. So we have a non-associative algebra. So O and V is a two-sided ideal, and the quotient algebra that denoted by N and V, that's associative algebra. And that's a linear operator theta on V reduced to an anti-automorphism of A and V. And also for different N, so we have this algebra epimorphism. So this gives us an inverse system. And here is a level N vacuum space. So again, let W be a weak model and a non-negative integer. So this is the level N vacuum space. So here, so if we don't assume V is homogeneous, we just put this inside XL0 acting on V. Yeah. So this is the level N vacuum space. And then, so this is the result, and from weak model to AV model. So this is the action. So this is to give you the global action V over W, by define this, basically is the degrees mod 0 action, and then the associativity acting on the level n vacuum space, and this is reduced to a model for the social algebra in Lie. So that this direction. Okay, and of course the other directions are more complicated. So here we will need some result here about level n vacuum space. In the definition for vacuum space, only we use one layer, and if the degree is less than negative n equals 0, but this will tell you, give a generalization, and in general, this is higher degree, give that. So this is always true. And basically, this will give us a good filtration. And also, especially, this one will tell us, so submode will be locally nilpotent on the vacuum space. Okay, so this level n, all level n vacuum space give us a bending sequence. So here, so we consider all the union, because this is the ascending, this is union. So this union is a submodel of W. And we just want to say L positive 1 is locally nilpotent on this submodel. Okay, then we have, so okay, and originally for n greater equal 0, we define the level n vacuum space. And then for negative integer n, we define just 0. And then we have this compatibility for that. So just degree and shift that. Okay, then of course, and from there, so we can have associated graded model. So for that, so this has become ungraded. We can say this is ungraded weak model, or usually called admissible B model for that. Okay, now, and okay, so here's some factors. So this is, we will use some classical duality. So just to quickly remind us, so for every fixed positive non-negative integer n, we have a first non-associative algebra on V, and we have a two-sided ideal, and we have quotient algebra as associative algebra. And also at the same time, so theta is order 2 bijective linear operator on V, and that preserves the ideal, and this gives us an anti-automorphism. Then we consider this as a classical case. Just to consider, we have a non-associative algebra with order 2 bijective linear operator. And here we don't just a model, we don't consider model, we just consider, let's just say, action with a left action, okay, for other property. And then for the dual space, W2, and we use this theta to define the action on the dual space. That. And the next one, of course, so general principle. And for W, you consider W star, and for subspace W0. And one thing you consider W, as a quotient space, then you consider dual space. So the dual space for this quotient, of course, is a natural subspace. Naturally, is a subspace of the full dual. So simply, yes. So, and to continue with this assumption, so then, so the dual of the quotient inside the W dual is astable, if only if actually W0 is a stable subspace of W. This is a simple linear algebra for that. And furthermore, in dual algebra, if we assume that G is ideal, like a previous one, and suppose theta preserve J, and such that the quotient is associative algebra, becomes an algebra anti-automorphism, then go further. So W0 subspace such that the dual of the quotient is astable. Assume this condition can reduce to the quotient algebra, then, and that ideal will annihilate the quotient space. And furthermore, And the do space quotient is a model for the quotient algebra if only if the other part, W over W0 is a model for the quotient algebra for that. So this is the duality we are going to use. Okay, so now to Dong Jiang's result. So let W be a weaker V model, M and just non-negative integers, a pair of non-negative integers. So we use this as O n comma M. Here is a dagger of W, just linearly spanned by those vectors. And we circle NMW, just this. And furthermore, and define the prime, O prime, and just add more, your addition to this dagger, just add this L minus 1 plus L0 plus M minus N, this as operator, the image of this operator on the W. And so, okay, and here, and Don Jiang also introduced a lot of two more subspace of V, double prime, 3 prime. Here, I will not mention the detail. I will not use this part, so I just mention. So ONMV is just all the sum, and AN comma M is the quotient of that. And the result is that the quotient space is a left-right ANV and AMV bimodel. Left-right means left ANV model, right AM model, and a commute for that. And also, it's proved that by Dong and Jiang that actually, so when M equal N, okay, so that's the O equal O prime. That means double prime, triple prime, all inside 1 prime. And also, they believe that maybe this is also true in general. And in this work, so we basically motivate by connection with regular rotation. So we only consider directly is the quotient space of W by the first one, just the dagger. So just means we defined as a V circle, that's MN W for that. And for this one, for the diamond, that's including that L minus 1, L0, and M minus that part. And so we will prove that both actually, so A and B, AM bimodels. And so this will kind of indirectly confirming Dong and Jiang's like a conjecture or something. Okay. So here quickly and do the review the regular rotation. And V is a vertex VOA, and W is a weak model. And so this is from Franco Juan Labasi about the country green do story. So for any weak model, we can define this as do, not a problem. And here, let Z be a non-zero complex number. And then, so this is the so-called regular rotation for that. So this is depends on W, and this non-zero complex number Z. This consists of all the linear functions on W, satisfy the following conditions. So that depends on every vector inside V. So there is a negative K such that, so okay, you have this as do vertex operator acting on F, and then turn X minus Z to some power K, and inside the Lorentz series. This is simply tell you the shape of Y star V acting on W. Simply means that guy is like a fraction, denominator is X minus Z to K. That. So they come here. Okay, and then we define action to get model. So for V in V and F in that space, and so this is the right action. So first, and we consider that guy. So basically, this is the analytic continuation for that. So only this, we mentioned that x minus k and time that is basically like morphic for that. Just a Lorentz series, let's say that. This, you have the denominator. So basically, we expand in a different direction for that. This is the analytical continuation. Okay. So define this way. And then, okay, let's move on. Other direction. So this is related to the usual theorem. So here we can shift and shift the variable x to x plus z. Okay, let's pass this one here, just that technical. So the following equivalence. So f in the space, or one is, so there exists two non-negative k and l. So that's from the definition. On the other hand, if you shift, you get x plus z like this inside here. So the second part, the third part, we'll use this one, shift the pole, and we will define another action. So that is the second action. So we define this by using the shift this one, then we expand it the other way. So this is still an analytic continuation with the shift the pole. And then, so this is the old result here. So this is for any weak model, and they be any non-zero number. So we define like two vertical operator maps. One is YR, that's the right, and one is the left. So we get two weak V model structures. The model structure commute, that gives us a weak model for V tensor V. That's the result here. Okay, so this is just like a technical result. Okay, here's just a notation that, so whenever the contour is clear from context, so we'll drop Z. Okay, now the notions, we will see the vacuum space. So let M be a weak V tensor V model. So because we can embed V inside the tensor product in two different ways, right? One is for the first coordinate, second is for the second coordinate. Then we define vacuum M, NM, natural, MN, M, and for the first one, N for the second one. Require that. Define vacuum space. So it depends two parameters. Okay, so I will pass the bottom here. So because I wasted time at the beginning, so I passed this one. So basically, this is the level MN vacuum space. Okay. So as the first result, what we have is weak is W is a weak V model, general, MN, non-negative integer. And so we define this as a vector space here. So A something dagger is corresponding to this dagger. So, okay, and then, so this means here, so because we identify the dual of the quotient space as the subspace of the original dual space W. So for any F inside the full dual space, if this F inside is a subspace, for only if this is the condition. So just to tell you the shape, okay? So you tell you where the singularity is for that. And furthermore, okay, this is the identification. On the right side, exactly is the level MN vacuum space for the so-called regular representation with Z equal -1. the left side exactly is the dual space of the quotient, which is identified as the subspace of W star. So this is exactly coincide with this as a subspace. But on the model level, it's slightly different. We will need to deform the model structure a little bit. Okay, so we'll need this technical result, and that in general, suppose we have a weak model. So 0 is a complex number. This time it could be 0. And we consider this as new vertical equator map, and it involves L positive 1, L 0. And then this gives us a new structure of weak V model. Actually, the secret is the next one. If L1 is locally nilpotent on E, and the exponential to negative Z0, L positive 1 actually is, this is a V isomorphism from all the model to this new model structure. So that's actually the secret for this one. Okay, really, it's just by changing variable, use L positive 1. And then another result related this. So about the level N vacuum space, the two weak models are in general. So the level N vacuum space is the same, identical. And then this exponential to a negative Z0 L positive 1, so give us isomorphism. So that's it. So as a consequence, so on the vacuum space, you can define a new model, okay? But in this formula. Okay, so we will need just a notation for that. So we know that this vacuum space level and vacuum space is a model, but this is a slightly deformed one, isomorphic to that one. So what we used in the coming slide, we will use it for this regular rotation, YL with Z not equal positive 1, but the other YR, so we'll use Z0 equal negative. Okay, so now we define a new operation, and basically give us a product V and star with W depends on Mn, this one. Okay, is a variation from some product introduced by Chunyan and Jiang, so we mentioned later. So the key point is here is this is a duality. I want to mention a duality. So if you take a F and inside this is a dual space for that. So on the left side, acting on there, that's in the regular representation. That is the left action and shifted by the Z equal 1 acting there. And this is X to which V minus 1 exactly 0 mole. And this is, okay, this is covariant to the other direction, exactly this formula. So this is formula exactly from the calculation here. Okay, so this is simply tell us the left side, because we already have weak model, everything, this is naturally will be a model. The right side, if you go to the duality, so this will give us a right model. So that's the next one. So that's the result directly from the duality. So because we have the weak model, the regular rotation, so the left part is much easier to see. So that's, we have this. So the color is simply tell you. So we can define this as action and V on W this way. And then this will reduce it to right. Oh, this is right for AMV model for that. Okay. And then the other one, the next one, this is exactly the product introduced by Chunyan and Jiang. This is exactly the form. That's for the other direction. And then similarly, so this is for the, if we consider tensor product V, tensor V, so this is the right action, but this time shift. And with that Z0, that is the negative 1. So this is the duality. So this is duality, but this side involves that theta. Theta is anti-automorphism for the level n to algebra. So this is the class of that. So so this time, so you see that this will, the left side is a left model, the right side should be a right model, but this is up to, composed with the anti-automorphism. So this is also give us a left model structure. So that's the duality tell us now. So that's the action, the blue one, and that's reduced to a left A and V model structure for that. And the community also clear because we use the bimodal structure, V tensor V model structure, because both V actions commute. So naturally, so this is give us, so this is A and M dagger. So this give us a left-right model. So commute that naturally from there. Okay, so next refinement. So we want to say not just as vector space, but we want to talk about more that as model structure now. And on one side, we have a level Mn vacuum space inside the regular rotation or inside the W star, the do space. So we shift the action, we mentioned that, and the deformed action. So because the deformed one is negative one or negative one, so we use this notation. On the other side, and for the A and V stuff, we already defined the two actions. One, the second one, exactly the definition given by Chun and John. And the first one is slightly variation. So that's a duality. And then, so as A and V model, so this exactly the duality. Okay. That. Okay, then and it involves some other result related to Chun's and Jiang's result. Okay, I would go faster here. So of course, there's a relate to filtration. So okay, the union give us a submodel of that. It's about direct limit stuff. I will pass that. So also on the so-called regular rotation for that, we have a model. We will just use for the right factor, V. So the notation, we need that. Just for vertical operator, we write down this way. And then, so this is related to filtration, this lemma. Just to tell you, this is for level Mn vacuum space. So when we use for regular rotation, we have the right side operator. So this is how to shift the filtration. M is fixed, only shift for that N. And then, so we recall that we have that O prime. O prime consists two parts. One is for dagger, and then for the L-1, L plus L0 plus L minus N, the image for that. Okay, now, and we will consider more stuff. Okay, this is the conformal vector. W omega is a conformal vector. So this Chiral algebra will act on the dual space with this, we know easily. So, okay, now go back to regular rotation with the shift. So we write down both give us a model structure for Chiral algebra, commuting. So we write down a component in this form, L, positive one, and key thing is, the first one is L for left, right, R for right. And then, so the following relation hold if F in the regular rotation. And so L star 1 and this acting on F, this exactly equals to the 2 mod 0 via Chiral, the subtraction. That's a nice thing. Then consider duality on W exactly. This is L star 1 corresponding L negative 1, L0 corresponding L0. Okay, this is exactly this part. So this tell us the connection, indicate the connection with Troyans and Johnson notion for that O prime. And then furthermore, and okay, the identification. So relate to eigenvalues. So F inside that subspace relate to the quotient space by that's O prime. If only if, of course, first this is inside the vacuum space, level M and vacuum space, and also, and just bring the first one here. Okay, so that means if we fix the M, so this exactly is the eigenvector. If it's eigenvector for the difference of the two mod 0, we are sort of vector for that. And then we define this, we use this as a diamond for vacuum space. Exactly consists of those vectors F for that. Okay, so we know that this dagger vacuum space is exactly the dual space of the dagger, the quotient space of that dagger A for that. And then now, because the eigenvalue, if we fix the M, let n vary, you consider sum, this has become a direct sum inside the regular representation of that. So here I think that n as a box means summation of that. So this is to give us an ungraded or admissible model, an ungraded model that. Okay. And also we have the filtration. I mean, this is not the filtration, this is already graded. So shift the gradient this way. Okay. And that's naturally from the duality there. I mean, not like this is the calculation. And then we consider the dual space then. Okay, but okay, and we already inside the regular representation we have ungraded V model, and at the same time because on the right side is a AM right model. So now we consider dual space, and for that, okay. So we have the prime, we have a dagger inside the prime in the dual space, and of course, the dual of the diamond inside the dual of the dagger. That, and then, so this is the corollary for that. So use the duality. So the dual of the dagger actually is AMV and tensor AMV submodel of the dual of a diamond is the dual of the diamond is the dual of the is a submodel of the dual of the dagger for that. So this, which already identified with the level M vacuum space for that inside there. And on the other hand, use the duality because the first part, inside the weak model, everything that's easy. So on the second part, use the classical duality, so we can show that inside the dagger quotient space and the extra L minus 1, L0 plus L minus n image for that one, that gives us a submodel so that a dagger actually is the quotient model for that simple duality. Okay, and here furthermore, so we remember, so we have two parameters mn, and if we fix m and let n vary, so we already see that inside the regular representation, so we have a weak model, and now we consider duality, and it just consider a n w. Okay, so this is the define this as basically you define vertical interaction on W depends on Mn for that. And so this is basically means define linear operator UP depend on W that depends on Mn. Define this notion. So this is exactly the notion introduced by Chongyin and Jiang. And here, okay, this is the lemma, the connection. Again, we want to emphasize duality as long as we let V be inside the level Mn vacuum space that's identified as the dual space of this diagram. And then that the left side is the regular vertical operator action. And the right side here, originally we only consider A and B. Now we put them together, actually we consider V model structure. So here is P not necessarily the weight of V, so that's why here, general. And this is also the right side. So here exactly use the theta, the that's an inclusion system. So this gives the duality actually in terms of component. And then use the result again, duality again. So this is give us like the filtration property for old dagger for that. Okay. Okay, that's a filtration property. And then now with the dual space now, so we consider for A and M, we define the diamond for that A and M. And then this is the external direct sum. And we define this space. And of course, we know that each part is AM right model. So this together is still a right model. But this actually, so we'll see that this is exactly the gradient, the dual of something inside the control gradient and inside the regular rotation. Because we know that the identification before. And then we can use this duality again to give the mythical V model structure as a gradient U on this space. Okay, so here is the comparison. This one is the red one, dagger A. Here is the omega this inside the regular rotation. So inside the regular rotation, the advantage is we already have a weak model, everything relatively easy to prove. So we use duality here and we get it. Okay, first, and we can use the previous result. We can see that filtration property. Now this is not just a filtration, it's graded already. And then the definition now on that summations, the new space only depends on n, let n vary. So we have this is like filtration construction. Okay, exactly filtration construction for that definition. So you define vertical operator, the components BP, you act on each summon this way. Okay, and then this is finally we get this version of a theorem Chongyin and Jiang, this one. So we can just get corresponding weak model structure on this space. This is the external direct sum, but the motivation is from regular rotation. Inside there, we have a canonical model structure. And it's a weak V left V model structure, but at the same time, because M fixed one, from the right action, we also have a commuting AM action. So this theorem just tell you, okay, well, any weak V model W, any M, so we have that space, and we define this as a diamond vertical operator. Only things to match the vertical operator here, the shift this way. And then, so this is here to give you a weak model. That's exactly coincide with the control gradient due, the control gradient due of that model inside the regular rotation for that. Okay, I think I will just stop here. and a little bit of rush, and I apologize at the beginning, the technical problem of that. So I will stop here. Okay, thank you for your attention.
Thank you. Let's thank the speaker. Are there any questions? Or from the Zoom audience? Let me check here. No, I think... sorry, just a moment. Wow. Okay, now if there are no questions, let's thank the speaker again.
Thank you.
Yeah, thanks for the talk, and sorry about the technical issues.
I'm sorry for that. So just the new computer. Okay, I'll stop.
Okay, in that case, actually, yeah, you finished early, so we can probably in 5 minutes go on with the next talk, which is Chongying Dong.